Concorde is famous. People talk about its speed, its shape, and its place in aviation history. But there came a moment when another British jet quietly carried a role far more important than most people realize, one that helped make key parts of Concorde possible without anyone noticing. This jet was the BAC-111, a small aircraft that introduced new construction methods and brought jet travel into tiny airports with almost no equipment. So how did it do all of that? Why was the BAC-111 so practical? BAC-111 didn't look special. It didn't have an exciting nose, long wings, or sleek curves. Instead, it looked round, short, and almost cartoonish. And yet this jet, the BAC-111, turned into one of the most useful aircraft of its generation. People didn't expect it to matter much, but it soon became the jet that made flying simple, fast, and accessible for places that had never seen a jet before. To understand how, we need to start with what airports actually looked like in the early 1960s. It's easy to imagine big airports with glass walls and fancy bridges, but the reality in many European towns was very different. Some airports were little more than old military fields left over from the war. Many had short runways, tiny buildings, and no equipment to support modern jets. A lot of them didn't even have stairs for passengers to board, yet people in those towns wanted to join the jet age too, and airlines wanted to serve them. That gap between small airports and modern jets was huge. The 111 stepped right into that gap. The smart part was how self-sufficient the aircraft was. Most jets needed power trucks to start engines, air conditioning units to cool the cabin, and ground vehicles to load passengers. But the 111 came with its own built-in help. It had an APU in the tail which acted like a tiny engine that powered the cabin and helped start the big engines. This meant it could land at an airport with zero equipment and still turn around for the next flight. For the time, this was extremely advanced. Many airliners could not do anything unless a ground crew plugged in a machine first. Another helpful feature sat right under the tail: built-in stairs. The aircraft carried its own rear steps, which dropped down like a small doorway. Passengers could climb in without waiting for any equipment to roll up. Later versions even had front stairs too, which made boarding even faster. Airlines saw this and immediately understood what it meant. They could fly this jet into small towns, land, open the stairs, load passengers, and take off again, all without asking the airport for help. That level of independence made the aircraft a perfect fit for short, fast trips. This independence also changed the way crews worked. Typical jets of the era needed a large team, including a flight engineer. But the 111 simplified the cockpit so much that airlines only needed 2 pilots. The rest of the team was 2 cabin crew members, making 4 people total. And when the jet visited tiny airports, those same 4 people could handle nearly everything themselves. One pilot did the outside check, the other pilot prepared the cockpit, one cabin crew member greeted passengers at the top of the stairs, the other cabin crew member helped move bags because the aircraft sat low enough to be loaded by hand. It was all very simple, and airlines absolutely loved how cheap and smooth it made their operations. This jet also carried strengths that were not immediately visible. Its structure was tough, much tougher than its small size suggested. Engineers used advanced metal bonding methods to build parts of the fuselage. This reduced weak points and made it more resistant to stress and fatigue. Later, similar construction approaches helped engineers working on Concorde. Yes, the little 111 played a part in shaping the engineering behind one of the most iconic jets in history. Most passengers never knew this, but the connection ran deep inside the aircraft's design foundation. Another important thing the jet solved was the challenge of repeated takeoffs and landings. Short flights meant more cycles, more pressure changes, and more chances for wear and tear. The 111 handled this easily. Its landing gear could take hard hits on short runways, and its fuselage stayed strong even after countless flights. Other than that, it didn't demand constant repairs between trips. That reliability made airlines trust it quickly. But the real magic appeared in how it expanded travel for everyday people. Imagine living in a small town that never saw jets because the runway was too short or the airport lacked equipment. Suddenly, the 111 arrived. It didn't need fancy buildings. It didn't need expensive machines. It simply landed, opened its own stairs, and welcomed passengers straight from the ground. This turned remote places into connected hubs. Travelers who once spent hours on trains or buses could now fly directly to major cities like London or Paris in a fraction of the time. This new system created what many called feeder routes. A passenger in a town could board the 111, fly for 30 or 40 minutes, then transfer immediately onto long-range jets like the 707. Suddenly, being far from a major airport didn't mean the jet age skipped over you. For Europe, this shift was huge. Countries didn't need to build large airports everywhere. They just needed one good hub, and aircraft like the 111 handled the rest. Its timing was also important. The jet flew for the first time in 1963, beating famous short-haul jets like the Douglas DC-9 and the Boeing 737. Many features people later linked to those aircraft appeared first on the 111. It quietly set the standard long before others followed. And right as the 111 built these new networks, engineers in Britain worked on Concorde. The two jets couldn't look more different. One small and chunky, the other sharp and futuristic. But behind the scenes, their stories connected. How did this connection help in building Concorde? Why Concorde needed the BAC 111 first? To understand this, imagine Britain in the early 1960s. Engineers were designing two completely different jets at the same time. One was a fast supersonic airliner that required cutting-edge math, special metals, and new aerodynamics. The other was a small regional jet that needed to be tough, simple, and cheap to run. On the surface, they had nothing in common. One chased extreme speed, the other chased everyday practicality. But in reality, both projects were connected through the same test pilots, the same engineers, and even the same fears about metal fatigue and safety. The 111 ended up becoming a kind of training ground where engineers solved real problems that later showed up again during Concorde's development. One of the biggest connections came from a legendary British test pilot named Brian Trubshaw. Before he became the first British pilot to fly Concorde, he worked on the 111 test program. That meant he already understood how BAC built aircraft, what the engineering team worried about, and how far they could push a new design. When he later moved into Concorde testing, he carried those lessons with him. His experience directly shaped how later test flights were planned. Even well-known engineer Barnes Wallis, who is famous for some of Britain's most advanced aviation ideas, worked on both aircraft. So it was not two separate worlds. It was one team learning from two very different projects at the same time. Now this is where things get interesting. Concorde needed extremely strong structures. Flying through the air at twice the speed of sound creates enormous temperatures and stress on the fuselage. If the metal expanded or flexed too much, the entire aircraft could fail. So the engineers needed new building methods that were stronger and cleaner than traditional riveting. Cracks in metal were a nightmare scenario, especially after the famous comet disasters a decade earlier. The 111 became the perfect place to test new ways of building strong, crack-resistant structures. Instead of relying mainly on riveted sheets of metal, BAC used large pieces of aluminum that were milled and bonded into shape. This created smoother surfaces with fewer weak points, stronger joints, and better durability. The engineering team learned how the metal behaved under real flight cycles, how it handled temperature changes, and how it reacted during hard landings. These lessons were quite essential. Concorde later used similar bonding and machining techniques, building on what had already been proven on the 111. The small jet gave engineers confidence in construction methods that Concorde depended on for its entire lifespan. It did it without anyone noticing. But structural strength was not the only thing the 111 taught. It also taught engineers a lot about fatigue, the tiny changes metal goes through every time a plane pressurizes and depressurizes. A jet that flies short routes like the 111 goes through far more of these cycles than a long-haul jet. That made it the perfect stress testing machine. Because the 111 handled thousands of pressurization cycles without serious issues, engineers could prove that their new structural designs made sense. And those same ideas later went into Concorde's cabin structure, wings, and tail. Speaking of wings and tails, the 111 also revealed a deadly risk that engineers didn't fully understand at the time: the deep stall problem. During early test flights, the first prototype entered an aerodynamic state where the tail stopped getting airflow during a stall. The jet lost control and crashed. It was tragic, but it exposed a problem that no one had clearly identified before. From this accident, BAC engineers created several new safety systems, including the stick shaker that warns pilots of an approaching stall, and the stick pusher that forces the aircraft to lower its nose automatically. These systems eventually spread across the entire aviation industry, including the planes that shared the 111's T-tail layout. Why does this matter to Concorde? Because Concorde's aerodynamic team had to ensure their aircraft avoided similar dangerous stall behavior. They studied these findings, built new test models, and created their own safety margins using lessons learned from the 111 accident. Without those earlier discoveries, Concorde's engineers would have been flying blind into new aerodynamic territory. Another link that might surprise you is how the 111 supported the whole network idea behind Concorde. Designers knew the supersonic jet needed long runways and major airports. It couldn't land in small towns or on short airstrips, so Britain needed a smaller jet to carry passengers into major hubs, where Concorde could take over. That concept fit the 111 perfectly, and this concept is called the feeder system. The jet connected small towns to big cities. It carried passengers from small European airports into London or Paris, where Concorde would later depart. This made the entire supersonic plan workable. Without a reliable feeder jet, Concorde would have struggled to fill seats. Many airports simply couldn't handle Concorde's length, weight, or speed, so only a few large hubs could use it. The 111 helped solve that problem by linking smaller regions to those hubs. The 111 also proved that British engineers could build aircraft strong enough for repeated rough landings and high-cycle use. It even survived extreme accidents. One aircraft crash-landed on a highway after losing both engines, yet stayed intact enough for most passengers to survive. Two others in separate incidents survived bomb explosions and still landed safely. Engineers took these results seriously. They used them to refine structural assumptions and test new metal alloys for later aircraft. All of this meant the 111 wasn't just some small, friendly regional jet. It was a tough, experimental platform that taught Britain how to build stronger aircraft, clearer safety systems, and better structures. Why this brilliant jet lost to its rivals. So after everything the BAC 111 proved, there is one huge question left hanging in the air. If this jet did so many things right, why did it lose the race to its rivals? The truth is surprisingly simple. The 111 entered a market already filling up with cheaper options, and that one detail shaped its entire future. The McDonnell Douglas DC-9 came in at a lower price and delivered solid performance, which made airlines feel like they were getting more value for each dollar. And then the real giant arrived. The Boeing 737 entered production, kept improving, and kept growing into new versions. It became a series that airlines could keep buying for decades. That gave it the momentum the 111 never had. The 111 had excellent engineering, but its price tag pushed many airlines toward aircraft that did almost the same job for less money. And yes, that hurt. Airlines watch costs like hawks. A few million saved per aircraft can decide an entire fleet plan. The BAC 111 just stood on the expensive side of that line. But here is the twist almost nobody talks about. BAC didn't want to stay small jet only. They tried to go bigger. Engineers drew up the 211 and the 311, both meant to compete directly with new American wide-body aircraft. The plan was to build a British jet that could do medium to long-range routes while keeping the tough, reliable design philosophy of the 111. The early drawings showed a large cabin cross-section, two rear engines, and a layout that looked quite sturdy. And for a short moment, it looked possible. British European Airways showed real interest. Meetings were held. Designers worked on full-scale mock-ups. BAC even presented the aircraft publicly, hoping to secure government support. But this was also the exact time Europe was forming the early Airbus group, and that changed everything. The UK had to choose: put money behind an entirely British widebody, or join the new European partnership. The government picked Airbus. Funding for the 311 stopped instantly. Without that support, the project collapsed. And once the larger versions died, the 111 had no future path left. It stayed frozen in size while its rivals kept expanding into multiple generations. And yet, even after losing commercially, the 111 still shaped European aviation in ways most people never see. Its design lessons echoed inside early Airbus models, and its engineering culture traveled far beyond its own lifespan. Not bad for a jet that always got introduced as the small one. What do you think of this revolutionary jet? Share your thoughts in the comment section below. And before you go, don't forget to hit that subscribe button so you never miss the latest aviation updates. We will keep you in the loop. Goodbye for now.